And let's look at this. Okay, so those are all the basic identities. Okay, those are the ones that we need to know. And then here's what we're going to do to use them. Okay, here's what we're going to do to figure these out. So, let's see. Let's start right here at the bottom. It says Pythagorean identities are sometimes used in radical forms such as sine of u equals plus or minus 1 minus cosine squared u. Okay, it says Pythagorean identities, right? That's this list right here. Which of these three should we choose to try and figure out how they came up with this one right here? The very first one. Okay, now what did they do to this one to turn it into that one right there? Moved cosine to the other side, so we got sine squared u equals 1 minus cosine squared u. Take the square root. Now, when we're solving an equation using a square root, if we put the square root in there, we have to account for the fact that it could have been plus or minus. That's why the plus or minus is there. Okay? Same thing there. Any questions? Okay. That is an example of what the things are that we're going to do in this section. We're going to take these identities, these basic, these fundamental trig identities, and we're going to manipulate them. We're going to use them to figure out other stuff. So if we look at the next page, it says using the fundamental identities. It says the values of secant of u is negative 3/2, and tangent is greater than 0. What does tangent greater than 0 mean? It means it's positive, okay? And this is where this would come in handy. All students take calculus. If tangent is positive, what quadrants does it have to be in? 1 or 3. 1 or 3. Okay, so we've narrowed it down to 1 or 3. What if the secant is negative? Is the secant negative in quadrant 1? Nope. So which quadrant do we know we're working in? We know we're working in quadrant 3. That's where we are. Okay? Now it says find the values of all 6 trig functions. So the easiest one to find, if you know the secant, use the reciprocal and find the cosine. So the cosine is negative 2 over 3. Just flip that over. Okay? To find the other ones, we could draw a picture, figure out what the reference triangle looks like, label the sides correctly and all that sort of stuff. And that's pretty easy, and we already know how to do that. That is not the point of this section. Not the point of this section. What they want you to do is they want you to use identities. So we're going to grab an identity that involves something like a secant or something like a cosine, and we're going to find the other ones. So would everybody agree that this identity, the Pythagorean identity using sine and cosine, is a little bit easier to work with, or at least more familiar than the one that involves secant? I know the secant. I could use the one with secant and tangent, okay, but that one's a little bit more familiar. So if sine squared is the same as 1 minus cosine squared, this would be 1 minus, I know the cosine is negative 2/3, so I square that. That's 1 minus 9/4. That would be 9/9 minus 4/9. So I end up with 5/9. Okay, are we done? That's what sine squared is, right? So how do you figure out what sine is? Take the square root. Take the square root of both sides. Now, we'd need to put a plus or minus on here. So this would be plus or minus, radical 5 over 3. Except for we know what quadrant we're in, right? We're in the third quadrant. What sign does sine have? Negative. Okay, so it's got to be negative. So I've got secant and therefore cosine. I use an identity to figure out what the sine is. So I've got 3 of the 6. And then the other ones are pretty darn easy, because if I have the sine, what can I do to figure out the cosecant? What do I do with it? Flip it over. Okay, so if I look at the cosecant, Notice how the 3's on the top and the radical 5's on the bottom. And then once I have sine and cosine, I can do the sine over the cosine. So I have negative radical 5 over 3 over negative 2 over 3. So that's going to end up being positive radical 5 over 2. Does that make us feel good knowing that we're in quadrant 3 and the tangent should be positive? Okay, and then cotangent, we just take that and we'd flip it over. Okay, any questions? Okay, let's take a look at this next one. It says simplify that. So I'm going to move it to there. Okay, so if you'd look up here rather than looking at in your book, we want to simplify that. So when we say simplify, I mean, we just mean write it in a simpler fashion. Write it with less terms. Write it with fewer exponents. Cancel off common factors and things like that. Okay? Does anybody see something that we could do with this? We can factor out the sign. So if I take out the sign, so take out the sine of x, I'm left with cosine squared x minus 1. Does any part of that look kind of familiar? Cosine squared x minus 1. If you think of sine squared x plus cosine squared x equals 1, if I were to move this over here and that over there, I'd have cosine squared x minus 1 equals negative sine squared x. So here's what identities do for us. Okay, this is a bunch of mental hoops that we're jumping through. It's not like you do this all the time. Okay, but it does develop a different part of our brain. Okay, a part that says, you know what? If I see this, I can put this there because that's going to make it simpler. Or, might seem weird, there are times when we see this that it's actually to our advantage to write something like this. Now, we practice that a lot in trigonometry, and it seems like, my gosh, why are you making us do this? This is just a complete pain in the butt. It's because this type of idea, sometimes it's more convenient to simplify. Sometimes it's more convenient to make it look more complicated because of what it allows you to do. And that happens a lot in calculus. Okay? Just ask the students in my calc class that are struggling with their first assignment. So, notice that we do this. On this one, they actually pulled out the negative. That's pretty clever. I may not have thought of that. Okay? But you'll notice that in place of this, we're going to put a negative sine squared x. Multiply all those together, and there's your answer. I actually like this better than I like the way they did it. Okay? It takes a little bit more work to see what they did. Okay? Any questions? Okay. All right. Let's take a look at these next ones. The instructions on those are factor each expression. Okay. Again, look up here. Don't look in your book if you've got it open. Factor each one of those expressions. Does that look at all familiar as far as a factoring problem goes? We went over factoring in this class at the beginning, didn't we? Okay. First thing you do is take out. If you don't know these rules, you might want to jot them down so you don't forget them. First thing you do is you take out the greatest common factor. Second thing you do is you count how many terms there are. If there are 2 terms, there are 3 formulas that might factor it. If there are 3 terms, it's a trinomial, and there are a couple techniques we have for that. If there are 4 terms, what do we always use? Grouping, okay? And more than that, grouping. And the last thing we always want to do with factoring is make sure that we factored completely. How many terms here? 2. It's either a difference of squares, a difference of cubes. There's no way it could be a sum of cubes. This is a difference of squares. So remember that one, a squared minus b squared, a minus b, a plus b. First one minus the second one, first one plus the second one. So what's the first one? Secant. Secant of theta minus 1 and secant of theta plus 1. How many terms here? There are 4. 4? 3. Only 3. 1, 2, 3. 3 terms means it's a trinomial. Is this an easy trinomial, one where you can use guess and check, or is this a little bit more difficult? This is a little more difficult. Okay, this is a hard trinomial. So we used a technique called trinomial grouping. Okay, multiply those two numbers together. Negative 12. Are there numbers that multiply to be negative 12 that combine to be positive 1? 4 and negative 3, right? So if you've got 4 and negative 3, they multiply to be negative 12, and they combine to be that positive 1 right there. So here's what we do. We write this as 4 tangent squared theta plus 4 tangent theta minus 3 tangent theta minus 3. And then how many terms do I have? 4. And how do you factor 4 terms? Grouping. Now, if you can do this without doing this, okay, so that's going to be a tangent squared, a tangent theta plus 1, right? And then take out the leading coefficient, including the sine. They both have a tangent theta plus 1. And this is 4 tangent theta minus 3. If you want to write that one first and the other one second, that's totally okay, but those are the factored answers. Okay? Now let's take a look at what they did. Difference of squares jumped right to here. That's pretty good. It's of that form right there, so they just identified it as a trinomial. Didn't really remind you of how to factor those. So if you have trouble factoring a trinomial, you can use that trinomial grouping technique. Any questions? Okay, let's take a look at this one. This one's a little bit more difficult. And let's look at how they did it. So it says factor. Okay, do you see what's immediately wrong with this? Okay. I want you to jot this down somewhere or just lock it away in your memory. It's usually easier to work with the same trig function and the same angle, or change them into sines and cosines. So it's usually easier to work with the same trig function and the same angle, or change everything into sines and cosines. In fact, that's a technique that we use a lot. So same trig function is helpful, same angle is helpful, and writing things as sines and cosines in terms of sines and cosines can be helpful. Okay, now, did I just give you a step-by-step list of how to deal with these? Nope, they're just ideas, okay? On this one, we're not going to write this in terms of sines and cosines, because that's not the best thing to do. But we are going to recognize this. That's an x, and that's an x. So at least we're working with the same angle. That's good news. If we weren't, this would be a really, really difficult problem. But what I don't have is I don't have the same trig function. So if I can get everything in terms of the same trig function, that might be helpful. So the way we do that is, notice what's changed from here to here. What changed? What did they do? One of the Pythagorean identities, right? Okay, that Pythagorean identity, and again, if you have these memorized, that's great. If not, okay, remember it's 1 plus cotangent squared x equals cosecant squared x. Because if I have sine squared x, cosine squared x equals 1. If I go through and divide everything by sine squared divided by sine squared is 1. Cosine squared divided by sine squared would be cotangent squared, and 1 over sine squared is cosecant squared. So wherever there's a cosecant squared, this is what I can put into place. It looks like I'm making it more complicated, but what advantage do we have now? Same trig function, okay? And like I said, a lot of times that can be helpful. So We're going to do, let's see, take off the parentheses. There's the cotangent squared, there's the minus cotangent, and then put the two of these together, and there's a minus 1. Now it's a trinomial. Pretty easy to factor. The only way to make a cotangent squared would be cotangent here and cotangent there. Two numbers that multiply to be negative 2 and combine to be negative 1. Good? Okay. Is this hard? Is it weird? A little strange that you do stuff like this? Okay. We're not solving equations. We're not getting number answers. We're not figuring out how tall the Washington Monument is. All we're doing is we're doing some mental hoop jumping. Okay? Okay. Notice what they did on this next one. They want us to simplify what happened from here to here. Wrote it in terms of sines and cosines. Writing in terms of sines and cosines wasn't the right thing to do on the last one, but it is the right thing to do here. So I've got a sine, that stays the same. Cotangent is cosine over sine times cosine. Simplifying, we normally put fractions together. Now my question for you is, how did they go from this line to this line here? Very good. Common denominator. So we wrote it as sine t, and then I'm going to write cosine squared t over sine t. If you're going to put these together, what does this one need? Needs a sine of t here and a sine of t there. That's why we get sine squared. Didn't change that at all. That's cosine squared. Pythagorean identity gets us to here. Reciprocal identity gets us to here. Okay, now let's talk about this running commentary over here. Okay, these are called rationale. Oops. Those are the rationale. Okay, what would be another way to describe a rationale? Do you know what a rationale is? Explanation or reasons, justification. Okay, so whenever you make a substitution, whenever you change something, it's a really good idea to be in a habit of writing down what you did. That's a quotient identity. I would probably have written common denominator and add, so that reminds you of what you did. Okay, a Pythagorean identity was used to replace the numerator as a 1, and then a reciprocal identity. If you'll get in the habit of writing those down, it's going to be much easier to understand what's going on, and it's going to be much easier when you go back and study this or look at a problem where you made a mistake, figuring out where your mistake was. Okay? Any questions? Okay. Instructions here just say add. If you're going to add, you need to get a common denominator, right? So that is a factor, and that is a factor. What does this one need? What does this one need? Needs a sine. So that's why we've got a sine squared here. Distribute through, that's why we've got a cosine. Cosine times 1 would be cosine, and cosine times cosine squared. Now, what are we going to do with this? Replace it with a 1. Notice the rationale, Pythagorean identity. Cancel this entire factor with that entire factor. 1 over sine changes to cosecant because of a reciprocal identity. Okay? Any questions? Okay, got. Let's see. Let's look at one more, and then we're going to do some problems from the assignment. It says rewrite that so it's not in fractional form. Now, if you didn't look down below, and it said write that so it's not a fraction, it would be really hard. It's got a denominator. I can't just get rid of the denominator. Can't just not write it. Okay, but this is similar to doing something like this. If I have 3 over 1 plus radical 2, and I want to make the denominator so it's a nice number, what do I do there? Multiply by the conjugate. Multiply by 1 minus radical 2. What I'm doing is I'm multiplying by, remember, the conjugate means difference of squares. It's the factoring of a difference of squares. When I multiply these together, that middle term that's going to have a radical in it is going to be gone. I kind of do something like that on this next one. So what I need is, I need to get rid of that somehow. So if I multiply by 1 minus sine of x on the top and the bottom, what happens is the denominator is a perfect, or is a difference of squares. It's 1 minus sine squared x, and the top is 1 minus sine of x. Now you'll notice the instructions said, make sure it's not in fractional form. I just made this more complicated. That looks better than this right here, unless you consider what this is. It's cosine squared. So this is 1 minus sine of x over cosine squared x. Oops. And then look how clever this is to finish this off. Break it up into 2 pieces. So if you have to write it so there are no fractions in it, break it into 2 pieces so that we've got a 1 over cosine squared, because do we know what to write for a 1 over cosine squared? Secant squared. And then be really clever about this one. So that first term's really easy. This one right here, you have to think about it this way. Again, we don't do this very often. Our brains are really good at simplifying, not very good at making things more complex. So what I do is I think of this as 1 times the sine of x over cosine of x, cosine of x. Now, if I wrote 3/4 times 7/5, that's 3 times 7 over 4 times 5, right? But this is an equation. Can't I go both ways? If I had a multiplication problem on top and a multiplication on bottom, couldn't I break it into 2 fractions that are being multiplied? And that's why that's advantageous. I think of this as 1 over cosine times sine over cosine. So there's a tangent and there's a secant. And now we have something that's written with no fractions whatsoever. We usually like that when there are no fractions. Okay? Tough problem, but good practice doing something that we don't do very often. Okay? Using rules like this in reverse. Breaking fractions apart rather than putting them together and simplifying them like we normally do. Okay? Any questions? Okay. If you look in your book on the next page, that's the last page of the notes, or of the explanation in this section before you get to problems that you need to do. Okay, we're going to come back and we're going to look at this one maybe before we leave, but let's go ahead and look at the assignment. What's the first problem on the assignment? Okay, let's grab problem number 1. It says use the given values to evaluate, if possible, the remaining values of the trig function. So they did us a huge favor here. They gave us sine and cosine. What one would we figure out next? Okay, cosecant and secant. So cosecant of x would be 2 over radical 3. Am I worried about you rationalizing the denominator there? Not so much. Secant of x. What would the secant be? -2. Okay? Stop and think for just a second. Don't look anywhere. Don't look at somebody else's paper. What quadrant are we in? Quadrant 2. Quadrant 2. Because the sine is positive in quadrant 2 and the cosine is negative. Okay? And what else do we need to find? Tangent. Put the sine over the cosine. Okay? So tangent of x would be equal to radical 3 over 2 over -1/2. Flip that over, so that's going to be -2, so cancel that off, so negative radical 3. Okay? Shouldn't it be negative in quadrant 2? Absolutely. And once you have that, the last one you need to figure out is cotangent. Okay? Okay, you do the next one in that set of instructions. Pick the next problem in 1 through 14. Go ahead and do that. And please don't rely on any common angles. Figure them out for yourself using the identities. I believe it's the Greek letter phi. Are you on 7?
Yeah.
Excellent. Okay. We good with 3? 3 is pretty easy, isn't it? 3 is almost like problem number 1. How come? Because they gave you the sine and they gave you the secant, so flip it over and you've got the cosine, and then you're back to problem 1, right? Okay. Also, you should recognize those ratios. Those should look familiar. Those are from common angles. Take a look at number 7. Isn't 7 the next one? Are those ratios that look familiar? No, and neither is the symbol. This is the Greek letter phi. I'm pretty darn sure it's phi. I don't have all of them memorized, but I'm pretty sure it's phi. Okay? Just we use Greek letters to represent angles. Okay? So, I've got the secant and the cosecant. My argument is this. This problem is almost identical to problem 1. Why? Noah?
Because it pretty much gives you the reciprocals of the sine and the cosine.
Right. So you can immediately take this and write down the cosine of phi is 2/3. You can take this and immediately write down that the sine of phi is -5 over 3 radical 5. Now, should you simplify that? You probably should, and let me show you why. If the radical here is the same as the number on the top, this will always happen. Watch what happens when I multiply and rationalize the denominator.
Oh, I see.
I get a negative 5 radical 5 over 3 times 5. Whoops, 3 times 5. That should be a times. So then I can cancel those. I end up with a much better looking expression with fewer parts to it. So this is going to be the same as negative radical 5 over 3. So I've got the cosine and I've got the sine. And then once I have the sine and the cosine, I've got the tangent and I've got the cotangent. Okay? Good there? Okay. Take a look at the next set of instructions. What are the next problems on the assignment?
So
15.
yeah.
What else in this section? Didn't I give you a couple of them? 16, 17, and 19. Okay, let's take a look at 19. Don't look at anybody else's paper. Look at yours. And it says you've got to match that one up with one of these up here. So maybe it's a 1, maybe it's a negative 1, maybe it's a negative tangent. Maybe it's a tangent, maybe a cotangent, sine. If you have all the identities memorized that I asked you to memorize, if they're still ticking around in your head, which wasn't that before Christmas? Hasn't that been about a month? Would it be a good idea to go back and look at that review sheet that I said, get this memorized? Okay? Now, if for the time being, everybody listen, look up here. Look up here, please. If for the time being you're flipping back and forth, or you've got a cheat sheet or something next to you, that's not the end of the world. If that's still happening a couple days from now, that's trouble and you will have difficulty on the test because you're not taking time to get those memorized. There's nothing wrong with double checking once in a while, but you have to take the time to memorize. If you don't memorize those, you are crippling yourself for trigonometry. Okay? There's some things you just have to know and know quickly. It's like knowing your times tables. You wouldn't want to be in this class if you didn't know what 2 times 4 was. Like that. Okay, that's the way you want to get identities eventually. It's 8, right? Who thinks they know the answer and can explain why? Meaning give a rationale, a justification, a reason. Lynn? Okay, Lynn says it's negative tangent, and she is right. She could have got that by guessing. We're going to be impressed if she can tell us why that's the answer. Okay, thingamabobber is great to write on a test, but it takes you a while. What would be better than thingamabobber? You're on the right track. I know what you're talking about. Tell me how you rewrite this. Negative sine of x over cosine of x, and then that equals negative tangent of x. There's the work. That's very convincing. I can see what she did. What would be awesome is if she could name it. Other than thingamabobber. Anybody remember what they're called? Odd even identities. Odd even identities. Very good. Okay? Okay, now, if you can't name it but can do it, is that okay? Yeah. Is it better to be able to name it so you can explain what's going on? And so when you're in a calculus class and somebody says, hey, we're using an odd even identity or a reciprocal identity, and then they plow through the rest of it, you're not going, holy crap, I don't know what they're talking about. You've got a name with the concept. Everybody good? Okay. Take a look at that next section. Which ones did I assign in 21 through 26? All of them? 21 to 22? 25. Okay, so 5 out of those. Okay. Jordan, pick a number between 1 and 5. 3. Look at number 23. Look at that one. Great problem.
Yeah, it is a great problem.
We would expect nothing less from you. Okay, I'm not making you do. Everybody think about this because everybody's responsible for getting this done. let's stop and think here for just a second. We've gone over combining fractions, pulling them apart. We've done some factoring. We've changed using identities, so we've got all in terms of sines and cosines maybe, all in terms of the same trig function maybe. Another general rule that doesn't always work, but something that you might want to think of is, if you have a trig function squared, you might want to think about using a Pythagorean identity. That's another thing you could write down. If you have a trig function squared, you might, and underline might, want to think about using a Pythagorean identity. Maybe that would make the problem simpler. Not always, but maybe, might. So, this has weird stuff. It's got secant and tangent, which are not our favorite. And it doesn't have squares, it has stuff to the fourth power. Has stuff to the fourth power. It has, no, what did you say?
2 squares.
It has 2 squares. It has secant squared squared and tangent squared squared. And in fact, let's think about putting all this stuff together that we've talked about today. There are 2 terms there. If there are 2 terms, I could factor it, couldn't I? I could factor it. And if I factor that and think of this as secant squared squared and tangent squared squared, then this would be secant squared minus tangent squared. And this would be secant squared plus tangent squared. Now I have some squares and some things that look a little bit more familiar. If I have a trig function squared, maybe I want to use a Pythagorean identity. That Pythagorean identity would be this one. It would be, let's stop and think for just a second. It would be tangent squared plus 1 equals secant squared. Isn't that the Pythagorean identity with secant and tangent? How does that help us here? Yeah, wherever there's a secant, what could you replace it with? You could replace it with a tangent squared plus 1. So let's be careful about this. This isn't the only way to do this, and there are some people that get frustrated with that there's not just one way to do things. No, this isn't, when you add them together, it's not 1. Because if you move this over here, it would be a negative. So you got to be careful with that. Okay. This isn't the only way to do it, but take a look here. So this is tangent squared x plus 1. Ooh, I'm gonna go ahead and write this. Tangent squared plus 1 plus tangent squared. And this is where it gets a little bit frustrating. What happens right here? That goes away, so this is just a 1. So what am I left with? I'm left with just this or just this. Which of those 2 is in the list of answers? This one, not that one. Okay? There it is. Okay? All right. Here's what I'd like you to do. I would like you to read, well, do as much of the homework as you can. The only type of problem that we haven't covered is this one right here. And I would like you to read this example. So read example 8. Do as much of the assignment as you can. When you come tomorrow, we're going to talk about example 8. Or what I'd love is if one of you would talk about example 8 and explain it to us. Okay? And then you can have the rest of the time to work on the assignment. Hopefully have no homework over the long weekend, right? Because we got Monday off.